Welcome to Dialogues of Discovery, a platform where we bring you conversations with visionary thinkers and trailblazers who are shaping the future. If you are curious, passionate, or just figuring it all out, you are in the right place.
Each episode brings you insights, experiences, and advice from the lives and minds of remarkable people, scientists, innovators, and creators, so you can get inspired, explore, and start carving your own path forward. Listen on to uncover more.
Today, we have the pleasure of welcoming Professor Debarati Chatterjee, an astrophysicist and full professor at the Inter-University Center for Astronomy and Astrophysics, more commonly known as IUCAA in Pune. She is the first woman to achieve this milestone in the Institute's 37-year history. Known for her pioneering work on neutron stars, magnetars, and gravitational waves, she is now leading IUCAA's Neutron Star Gravitational Wave Research Group and mentoring the next generation of researchers.
As LIGO India's Education and Public Outreach Chair and Director of Pint of Science India, she engages citizens and students like us with the wonders of black holes and multi-messenger astronomy through multilingual talks and festivals. She's a strong advocate for women in STEM, and we're excited to dive into conversation with her today.
So, Professor, our first question to you was, can you tell us a little bit about what really initially drew you towards theoretical astrophysics? Like, it's a very broad field, it's a very interesting field, but at what point did you know that was the field you wanted to walk into? And when did neutron stars in particular become your central focus?
Sure. I would love to share my journey. So, actually, it was very much by chance. When I was a young student like you, I used to watch a series called X-Files. I don't know if you've ever heard about it. Maybe you can Google about it. So, it was about genetics, and there was someone called Scully, and she was so amazing that I wanted to be a geneticist. So, you can imagine it's also called the Scully effect. Actually, a lot of women in those days, the young girls wanted to be like Scully. So I thought, okay, what is the field I should study to get into genetics? So I thought of different fields, and I thought, okay, why not physics? And then I joined my bachelor studies at St. Xavier's College in Kolkata in physics. And then when I started to learn more about physics, then I came across quantum physics and electrodynamics and also all these interesting aspects of theoretical physics. So I was already, my mind was blown by these amazing fields, and I thought, oh, physics itself is quite interesting actually. And then I went on to do my bachelor's project at the Indian Institute of Astrophysics. But this was completely different. This was actually on observation, so it was on solar physics, trying to understand differential rotation of the sun. But I realized I'm not really somebody who enjoys data or modeling, so I wanted to do more fundamental physics. Then when I went to masters in also Calcutta University, then I came across more and more theoretical concepts like particle physics and general relativity and quantum field theory. And I was like, okay, I think I really enjoy doing complex math. And so I thought theoretical physics is something that really fascinates me. And also at that time, when during my master's, there was a satellite that was being launched by ISRO called AstroSat. So this was actually launched way later, but they started already doing workshops to inform young students about what is expected, what is the science behind it. And I attended a very nice neutron star workshop at the Tata Institute of Fundamental Research in Mumbai. And there I was completely fascinated by neutron stars because it was everything I ever studied. It was so complex and so beautiful because there was almost every field of physics in it. And still it was something that we can observe in across the electromagnetic spectrum, but still so difficult to model. And it almost is still until date as challenging as it was. So I was like, I think you already realize I like doing complex things. Complex things fascinate me. So I was like, okay, I'm not going to get bored with this topic. So I think this is something I really want to do. And here I am working on neutron stars.
That sounds absolutely wonderful. Okay, so from going from genetics to general fundamental physics and then finding the one thing that you find really interesting. So,
Right.
right now, your work covers a lot of things from neutron stars to gravitational waves to dense matter physics. And I would love to know what the most important questions that your research group at IUCAA right now are trying to answer and you find really interesting for the field that you're working in right now.
Right. So I think one of the main challenges of why of neutron star physics is basically that it spans many scales. Okay, it goes from infinitesimally small to infinitesimally big. It encompasses everything, and it's very difficult to model everything within one consistent formalism, because if you look at it like the zooming over the universe at different scales, so we understand the universe at different scales when you take snapshots of it, but it's very difficult to go from one to the other. And this is the major problem in neutron star physics. What we try to do is, so dense matter physics. So the other problem with neutron stars is that they involve the physics of the extreme. So it's not something that we encounter in daily life. It is way beyond what we can actually measure in laboratories in terrestrial experiments. So it is something that might help us in the future to understand how matter behaves as we go to extreme limits. This is really going beyond something that is within our capacity. So that is why we resort to theoretical modeling. But even then, there are problems like many body theory, which is impossible to solve. You may have heard about the three body problem, and here we are talking about many body physics. So these are very complicated things to describe even theoretically, and forget about like even answering questions that of things we observe astrophysically. So I think the main things that we are trying to answer is that how this kind of dense matter physics, the physics of the extreme, can be described in a consistent way that can explain the behavior of neutron stars across these different scales, and also how such models and such physics can affect what we observe astrophysically, whether it's multi-wavelength electromagnetic radiation like X-rays, gamma rays, and radio waves, or whether it is gravitational waves. It's not something we can observe, but also something we predict to observe in future. So I think this is the main thing that we are trying to address here. Yeah, and also there are a lot of different exotic physics that is expected to appear inside neutron stars. So it's a perfect testing ground for those kind of things as well.
So, just speaking of the dense matter physics that you were talking about, right? Like, let me deep dive into this a little bit. Something that I read about when it comes to neutron stars is the Hyperon puzzle, which I think you've also done some work on, which is about what is really in this core of a neutron star. And that remains a slight mystery or a slight challenge, because what is predicted versus what would actually work in terms of physical reasoning, it doesn't entirely match. Right? So, can you tell us what is the progress that has been made with respect to this challenge, and or what do you see as the most promising direction towards resolving it today? What are the tools? What is the direction in general?
First of all, I'm fascinated by the fact that you already know about this, because it's a very specific field, and a great job that you have grasped so much of the complexity. So the Hyperon puzzle, until very recently, it has been one of the most challenging problems in neutron star physics. So basically, when you have particle accelerators like the one at CERN, there are these heavy ion experiments where you collide beams and you produce a lot of different particles, and many of these particles are produced for fractions of a second, and then they disappear again, because most of the material that surrounds us is made up of only the lightest quarks. So if you break down an atom, then you go inside its nucleus, then you will encounter neutrons and protons, and then you break them down further, you will end up with quarks. And these quarks, the lightest ones, the up and down quarks, is what makes up everything around us. Standard particle physics says that there can also be more heavy quarks in nature, but we don't observe them because they are way too heavy to be produced around us. We don't have that kind of density on Earth. But particle physics experiments, there already matter is like twice or three times more dense than what you have around us. And we see these particles appearing out of nowhere. So hyperons are one of them. So they have these additional strange quarks inside them, and that is what makes them unique. So hyperons, kaons, they are produced in pairs and they disappear. And the only place we think that this kind of particles can naturally appear is the dense matter core of a neutron star. So that's where you expect to have densities which are even beyond what you have in particle accelerators. So that was the exciting possibility even for particle physicists to think that, wow, okay, if we have a natural cosmic laboratory, that's where we should expect to find such particles. And how do we understand that these particles are there? So we need to find some signature of these particles on something we can observe, whether it's mass or its radius or some kind of cooling or some other property like gravitational wave emission. So that is also what we were looking for. So in my group, we have done a lot of research as to what happens when these particles appear, how they will affect the observational signatures. Now the problem is, of course, these particles behave differently when you have them inside the particle accelerator or when you have them in neutron stars. They are slightly different environments. And it's not that we understand, already we struggle to understand their behavior on Earth, and it is even more difficult to describe their behavior in the neutron star. So we don't know how to map them, how to describe all these through theoretical models. And so I think the way forward is now that when we have more and more observations, this is particularly an emerging field called multi-messenger astronomy, where you have multi-wavelength electromagnetic observation, X-rays, gamma rays, and so on. X-rays, gamma rays up to radio waves. So these are already observing neutron stars. And also we can predict, according to general relativity, whether gravitational waves would be emitted from neutron stars and how that would also encode the behavior of these hyperons inside them. So what would happen? Like, would it affect the oscillation properties? Would it affect its collisions? Would it affect the object that is formed after the collision? So all these things are quite complex because some of these we are just at the tip of the iceberg right now. We have only 1 or 2 observations in gravitational waves, and for post merger it is already beyond the sensitivity of our current detectors. So there are only numerical simulations which have their own challenges. So I think we are still in a very let's say preliminary stage to make convincing arguments about it, but I think there is a lot of exciting possibility to try and look at different aspects, like, okay, if you have hyperons affecting its thermal evolution, then it should also be consistent with its gravitational wave signature. So I think multi-messenger astronomy gives us the broader picture, the big picture. So this helps in eliminate a lot of the parameter space that we have of uncertainties in our models and helps us to understand the physics better.
So that's very interesting, the way you explained that multi-messenger astronomy as a whole has a lot of potential. But going back to something you said initially, which is that the particles that you're trying to measure don't always last very long, for maybe fractions of seconds. And so it's very possible that your research might not always go the way that you expect. So I would love to know an instance where something like that happened and how you dealt with that as well.
Definitely. So research actually is all about adapting to new possibilities and new environments, because current research is something that can change in a matter of a second. If tomorrow there is an observation, maybe a huge neutron star, extremely massive 3 solar mass neutron star, it might actually rule out most of the models that we have today. So we always have to deal with it with an open mind, first of all, because you cannot say that, okay, this is our belief and we don't want to go against it. As a scientist, we always have to be open. So also I can share my PhD thesis was mostly about oscillations in neutron stars and effects of these interior particles like hyperons and so on. But then when I came towards the end of my PhD, there was a massive setback in the financial condition across the world, like a financial crunch, which led to setback in major mega science projects. So LIGO at that time was in the initial phase when it had not had any gravitational wave detection. And in fact, many people believe that gravitational waves would not ever be predicted because they are so small. General theory of relativity predicts that the length difference, the difference in the dimension of something when gravitational waves pass through it is like 1 divided by 24 zeros. So it's like detecting a hair on the moon. And many people thought that it will never be detected. Like, I'm talking about scientists. So at that point, many countries, including the US and Europe, they said, okay, we do not want to continue funding LIGO or Virgo because this is completely useless and it's very expensive. So imagine that when we came out as PhDs, we were excited to work on gravitational waves. And at that point, I could not find some project that would allow me to do that. So I moved towards this Hyperon puzzle, exactly that you mentioned, because at that time there were some discoveries of very massive neutron stars, which would suggest that such particles would be ruled out. So that gave some new, very exciting prospects. But then again, during my postdocs, also in different countries, I had to move. It's not just about geographic mobility, but also intellectual mobility. I worked in, like I said, nuclear physics, and then this was particle physics. When I went to Paris Observatory, so I moved to France from Germany to work on simulations. So there I was at the Paris Observatory, where it was a relativity group, and they were mostly mathematicians who were working on how to model neutron stars. And there I gained a lot of expertise in numerical modeling. So I think you have to be adaptive and open to learning new things, particularly when you're a student. Of course, we have our favorites. Like I said, I love neutron stars and gravitational waves, but it may not be that you immediately have some projects at hand or something that allows you to explore this. So I think for me that was a setback at that point. But eventually, like later, a few years later, when I was a postdoc, gravitational waves were discovered, and at that point even the LIGO collaboration was looking for experts who were working on this. And I would say I was lucky to be able to get back into doing what I loved. It would always not be possible, but I think as scientists we have to be open-minded to different possibilities.
Okay. Thank you for sharing that. I think it was very interesting the way that a lot of twists and turns not entirely always in your control when it comes to that kind of field. So zooming out a little bit now, right? We're talking about, like you mentioned, general theory of relativity, gravitational waves, modeling neutron stars. But thinking from like the perspective of anyone out there right now, not necessarily someone who is an astrophysicist or is a theoretical physicist, your work, it deals with some of the most extreme and distant phenomena in the universe. So, how do you think this research ultimately matters to anyone in their day-to-day lives? Like, what is that relevant?
I think this is a very difficult question for people who work on fundamental physics. I think like even experimental physics or data analysis might be closer to reality than it is for fundamental physics. But what I would say is that, okay, I can mention a few things here. So one is gravitational wave astronomy in general, for example. So it involves many different fields. It's very multidisciplinary. So to give an example, gravitational wave detection would not be possible without, I mean, of course, it needs a very thorough understanding of general relativity itself and fundamental physics, but it also requires a lot of experimental expertise in lasers, optics, suspensions. So there are many engineers who have been working on this, and the offshoots from gravitational wave astronomy are so many that, I mean, for example, right now the LIGO-India, detector is being built in India. So that building the detector at such sensitivity, because it's one of the most precise instruments in the world, would place India at the forefront of technology, because this is really the technology of tomorrow. Like the coatings on the surface of the mirrors are so precise and so at an advanced level that this is even going beyond what we have the most advanced spacecrafts right now. So we are really talking of the future of technology here. So I think I would say this is like, if you focus on fundamental physics, this may not be, I may not be able to give you a straight answer like that, but I would say that everything came from fundamental physics, right? So science and technology go hand in hand, but technology is an application of fundamental science. So if you know about the stories like microwave and the discovery of even pulsars itself, they were serendipitous. It was not targeted. So I think fundamental physics is something that allows us to play around
knowledge
with
that
our
understanding
game
of
from
physics
that
itself
can be
and push it
applied
to
the
the
knowledge
later
that we
into
gain
building
so that
something
can
bigger
be
better.
applied
So
later
I don't
into
think
building
it may
something
be
bigger
applicable
better.
just
So
to
I don't
tomorrow to
think
build
it may
something
be
right
applicable
now,
just
but
to
I think our
tomorrow to build
understanding of
something
what
right
happens
now.
when
But
you
I think
have
our understanding of what happens
temperatures,
when you
magnetic
have
fields.
superfluidity going beyond our current knowledge, how that can enrich our understanding and how we can apply that later to some other technology. I think that would be my justification of what I do. But of course, curiosity drives us all. I think we are just plain curious. That's also there.
So, like you said, despite the fact that it may not be immediately applicable, there is still a lot of interest, and there's a lot more people that are looking towards astrophysics as a whole to work in. And you said that LIGO was, if not on the verge of a breakthrough, then had the potential for a really big discovery. But at the same time, this requires a lot of things, from funding to interest from other people to people actually working in the field. How would you say you view the current state of astrophysics research in India? So, from key gaps to any changes, or whether it's structural or cultural, in how India is viewed globally as a position in astrophysics.
So that's a very interesting question. So a lot has changed since I was a student, for the better, I would say. I can talk about good and bad things both. So one thing is that I think globally right now people are that like education in India is very robust, and people are, every colleague I know has an Indian student right now, and they are, all of them boast saying that they are doing very well. I think our education system empowers us. It's wholesome. It's not very focused all the time, but I think it gives us a very good general picture and a solid foundation so that we can almost take up everything. I think Indian students are doing very well abroad also. So I would say we are lucky in that way. But again, when it comes to fundamental research, there are pros and cons. In some fields, so I have learned from my colleagues who are particularly doing experimental physics, they say that experimental physics, of course, it requires a lot of equipment, it requires a lot of funding. As we know, it's not the richest country, so of course there are limitations to that. But many researchers now are actually winning a lot of grants and awards and fellowships, which allow them to buy equipment, set up labs. Many colleagues of mine who have worked abroad as students or postdocs are coming back to India and setting up their labs. For example, one of my colleagues just got the Max Planck Research Group fellowship or grant, which allows them to set up a lab like in Germany, but in India. So I think this kind of thing is great because they are bringing back the expertise to India. In theoretical physics, luckily, I don't have so much of restriction because I do theoretical work on paper or on the computer. So as long as I have fast internet and I have, okay, we do require high performance computers. That is also expensive, but I think India is doing well in that. Even we have a lot of support from the national supercomputing mission right now. They have had meetings with us to understand what are our requirements. So I think from that ground, we are pretty much doing very well. But in general, I think in general in the world and also in India, there is currently a trend going towards data analysis than fundamental physics. And the reason is that, of course, if you look at it, like there are right now so many missions out there which have so much data, and we really need people to process that data and come to conclusions about and analyze the data. So in fact, this is why there's also a lot of trend going towards AI and ML, so machine learning and artificial intelligence, because there's too much data and we don't know how to handle it. Of course, so I think definitely the future, IUCAA, when I joined it, it was still, I think the last few years when it was still a very theory dominated institute. And over the past 4 or 5 years, I have seen that the trend has moved towards observation. I think I'm one of the few who are doing theoretical work now. Also, even in theory, more and more people are going towards simulations because this is something easily, I think, justifiable to funding agencies and so on. So there is a lot of simulations that are gaining more and more popularity. And I would say most Indians, at least in reputed institutes right now who are being hired, they still work in international collaboration. So I think India is viewed quite highly with regard to that. Most of us are members of global international collaborations. We are, many of us win awards and we are quite reputed in that. So I think India is doing very well in that. But I would say I also interact in universities and smaller institutions in not big mega cities. So I would say there, of course, I have seen many have limited access and limited. It's not, I would say, not about access, because I think if you have internet now, even from your phone, you can check what research is going on. But I think it's probably because of less participation in conferences or less access to discussions and understanding of the current scenario. So sometimes I see that the research is lagging behind. So many of these people come as associates also to IUCAA to understand what is the current scenario of research. But I would say that in that case, one really needs national support. Like many universities have very long hours of teaching, for example, and there it would be very difficult for a professor to give lectures and have students there and as well as conduct top class research. So I think in that aspect also, the institutions, if they want to have good researchers, they would also have to give some freedom and some time to their professors so that they can nurture that. So yeah, I think I have like mixed feelings about all of it, but I think right now students are doing very well. So in our times, I think projects, I mean, I did it out of curiosity, but I see more and more people doing projects and more people who are serious. I'm already very impressed that you know about the Hyperon puzzle, and like people are curious. Also, there's much more access to YouTube videos, to a lot of portals, education portals. So I think this is a great trend. But another trend I dislike is that there is some kind of a misconception that just going abroad is going to give you a great exposure. So right now I see more and more students leaving India very early, already at bachelor's or master's and going abroad. Many of them, I'm sorry to say, actually drop out of academia, like because I would say that I went during my PhD, because I went time with a DAAD grant and I was already doing my PhD. So I had enough expertise that I had gained in India, and then I had an exposure abroad. So this was great for strengthening my confidence and giving me an international exposure and network. But a lot of people are going very early now, already at their bachelor stage or master stage. And I think at that point it could get very confusing or even very distracting. And I see a lot of very brilliant students going abroad and getting quite lost. And many of them apply to me later saying they would like to join for PhD and all that. But I think once you get disconnected from India, it becomes very difficult to come back. So many people are dropping out of academia. So I think one needs to also take into account that we have a solid foundation of PhD opportunities, master's opportunities also in India. Of course, going abroad, I would say that it does give a good exposure, but it's not necessarily that just leaving India is going to put you on a very advantageous position. So I think one should really weigh the pros and cons about making a decision about that.
Yeah, I think that's interesting. You encapsulated, like, there's so many factors when it comes to the landscape, not just education, but also the resources, infrastructure. And I agree, while the education situation is improving, there is limited exposure to the fact that, hey, this is happening, discussions, conferences, things you can participate in. I mean, we are two lucky high schoolers who have the opportunity to talk to you right now. Not everyone does. So, kind of leading forward to that, this is the last question that we have, which is there are a lot of students that are interested in theoretical astrophysics and fundamental physics. So, what are those skills, habits, ways of thinking that you would say matter most if they really want to get into this field and contribute in a meaningful way?
Yeah, I think theoretical astrophysics, like I said, is very, very exciting. But one has to keep a tab on reality because, like, you may have heard about people getting carried away with string theory and modified gravity. I mean, I would agree that they are extremely exciting fields, but one also needs to keep in mind that currently the trend is going towards a lot of observations, like a lot of data, because we do have the capability now to such to space or build such detectors, which we didn't have 10, 15 years back. So now, as soon as you write a theoretical model, the question immediately pops up that is it compatible with the current observation? So this is why a lot of models are ruled out and so on. So I think theoretical physics is very exciting, but one should keep in mind that one has to also be able to explain the current observations with it. I would say, so about developing, you said about habits and so on. So if I want to give an advice in general, I would say that one needs, in theoretical astrophysics, the things one really needs is a very good analytical skill to go from step one to step two. Logic is very important here, logic and analytical skills, patience, of course. And I think one has to have a broad, it always helped me to have a broad overview of different fields. For example, today, if you're working even in particle physics, there are so many problems that are related to dark matter, and those are also relevant to cosmology and neutrino physics. So as the trend is going more and more towards the multi-messenger aspects, I think it's very important to have a very good broad overview of what is going on in the different fields across the different scales. And even collaborations are also the way to go. I mean, gone, I think, are those days when you sat in an office and you were just solving equations on your with pen and paper. I think because right now, I would say even in neutron star physics, there are so many complexities. It's almost impossible for one person to know everything. So we need to talk to more and more people because all the fields are advancing at a very high pace. You know, they are really progressing very fast. So it's important to keep up with what is going on in the different fields, have a very good idea so that you understand what are your limitations, what are your prospects of your theoretical skills. Yeah, I would say that summarizes it.
Thank you. I think that's actually really good advice because you were very specific. That's actually really helpful for someone who doesn't really know what they're going to do. And
Right.
like Aashna said, that was our last question for the day. Thank you so much for taking the time out to have this interview. We both really enjoyed the conversation and we all learned a lot from it as well. So the stories you shared, your insights, and Your belief in the future of fundamental and theoretical physics. It's been extremely inspiring, and I'm sure they'll inspire our listeners as well. Thank you.
Thank you.
Thank you for joining us on this journey of ideas, inspiration, and innovation.
We hope this conversation sparked curiosity in you and reminded you that behind every great discovery is a human story of passion, purpose, and persistence.
Until next time, stay curious, stay inspired, and keep learning because the future is being built by the questions you ask today.
This is Dialogues of Discovery, signing off.